Hello everyone, thanks for watching this video. I'm Chen, a PhD student from University of Pennsylvania. I'm going to present our recently developed framework of learning Lyapunov functions for hybrid systems. It is a joint work with Maria Fazliab from Johns Hopkins University, Manfred Marari, Josh Papas, Victor Preciado from the University of Pennsylvania. Hybrid systems have received a wide interest from the control community in the last decades due to their ability to describe systems that are characterized by the interaction of discrete and continuous dynamics in a rigorous mathematical formalism. Indeed, hybrid modeling techniques have played a fundamental role in the design, analysis, and control of cyber-physical systems, robotic systems, etc. However, as nowadays hybrid systems are getting more and more complex, we need to rethink about the existing tools and develop new techniques to address the challenges emerging from the novel application scenarios. As a motivating example, let's consider robotic systems in closed loop with neural network controllers, synthesized either through supervised learning or reinforcement learning. If we want to analyze the closed loop stability of such systems, what are the possible challenges? To be more specific, we may assume that the robotic dynamics is modeled as a piecewise affine system, and it is in closed loop with a feed-forward ReLU neural network controller. Existing stability analysis tools are mainly based on the piecewise affine representation of the system in order to solve a semi-definite program for Lyapunov functions. To apply such tools, we necessarily have to first identify the piecewise affine representation of the ReLU network and of the closed-loop dynamics. Although ReLU network is essentially a piecewise affine function, finding its explicit piecewise affine representation can be tedious or even intractable as its width or depth increases. Therefore, the existing stability analysis tools are not applicable to the neural network control system, since the required piecewise affine representation is very difficult to obtain. Such limitation holds in other scenarios too, where the interconnection of different classes of hybrid systems, for example linear complementarity systems, mixed logical dynamical systems, are considered. To overcome this difficulty, in this talk we propose a sampling-based framework for stability analysis of hybrid systems based on their mixed integer representation, which is usually easy to obtain for all the hybrid system models listed above. To formalize our problem, let's first review the notation in this work. We consider discrete time autonomous system x plus equals f of x, where f is a continuous function, x is a vector of the current state, and x plus is a vector of the next state. Without loss of generality, we can assume that f0 equals to 0, which means that the origin is the equilibrium of the system. A fundamental problem in dynamical systems is to verify whether an equilibrium point is locally asymptotically stable, and to find its region of traction. By definition, the region of traction is a set of initial conditions from which the trajectories of the system converge to the equilibrium point asymptotically. A widely used framework for stability analysis of dynamical systems is the method of Lyapunov. Specifically, consider the dynamical system x plus equals fx and a given region of interest, which is denoted by the calligraphic x here. Then the equilibrium of the system is locally asymptotically stable if there exists a function v of x, that it is positive everywhere on the region of interest, and it decreases along all trajectories of the system initialized inside the region of interest. Then v of x is called a Lyapunov function. Once we can find the Lyapunov function, we have a certificate of local stability of the system, and we can use the sublevel size of Lyapunov function to compute an inner approximation of the region of attraction. As shown in this figure, the green region denotes the domain of the dynamics, and the light blue region denotes the true region of attraction of the system, which is unknown to us. In this work, we first manually set the region of interest, which is a convex polytope containing the origin in its interior, to guide our search of Lyapunov functions. Then we search for Lyapunov function v of x satisfying the above two constraints for every state inside the region of interest. If a Lyapunov function is found, then its sublevel set gives an inner approximate of the true region traction for the dynamical system. Finding Lyapunov functions for general systems is difficult and requires us to solve an infinite-dimensional optimization problem. Therefore, we need to restrict the search of Lyapunov functions to a finite dimensional function space. In this work, our contribution is a sampling-based method to synthesize Lyapunov functions for when the vector field f(x) of the dynamical system admits a mixed integer representation. Our framework is based on an iterative interaction between a learner and a verifier. The learner module does not make any assumption about the dynamical systems and merely uses a finite set of samples from the dynamical system to propose a Lyapunov function candidate. The verifier module then either verifies the Lyapunov function candidate or it rejects it with a counterexample, in other words, a state x star where the Lyapunov function is not decreasing. Then this counterexample is added to the set of samples so that the learner can refine its guess of the Lyapunov function in the next round. This interaction between the learner and verifier continues until we either find a Lyapunov function or certify that there exists no Lyapunov function in the entire class of functions considered. Importantly, this iterative algorithm is guaranteed to terminate in a finite number of iterations when a Lyapunov function in the considered function class indeed exists. When finding Lyapunov functions instead of searching over the function space, it is typical to parameterize the Lyapunov function using a finite set of parameters and search over the finite dimensional space of those parameters. Here we denote the parameterized Lyapunov function by Vxp, where p is a finite dimensional matrix parameter. We denote by f the set of all parameters that return a valid Lyapunov function. In our framework, we use a finite-step Lyapunov function of order k, which has the following quadratic form. Here P is a symmetric positive definite matrix to ensure that the Lyapunov function is positive everywhere, and zk of x is a concatenation of the current state x and the next k evolved states. We note that when k equals to 0, we obtain the classical quadratic Lyapunov function. We define the function delta Vxp as a difference function incurred in the Lyapunov function from the current state x to the next state f of x. We note that for fixed state x, delta Vxp is linear function in P. Using this definition of Lyapunov function, the set of all Lyapunov functions in the parameter space is given by the set of all symmetric matrices P that are positive definite, and that delta Vxp is less than 0 for all states in the region of interest. Since scaling P does not affect the satisfiability of the Lyapunov function constraints, we require P to be dominated by the identity matrix. We can readily verify that F is a bounded convex set in the parameter space, and we call F the target set. With these definitions, the goal is to find matrix P in the target set F. However, F can be empty, meaning that the class of Lyapunov functions candidates may not be sufficiently large. Furthermore, the set F is characterized by an infinitely many constraints, since we require the Lyapunov decrement condition to hold for all the states. Therefore, finding a feasible point is still not computationally tractable. Our idea is to localize the set F by a larger set F tilde, which is obtained by using a sample set of constraints that define F. In other words, we over-approximate the set of Lyapunov function parameters by relaxing the Lyapunov decrement condition to hold at only a finite set of samples, rather than the whole region of interest. Using this localization method, the learner module is charged with the task of finding a good feasible point inside the localization set F tilde, and the verifier module refines F tilde by finding counterexamples at which the Lyapunov decrement condition fails. This process continues until we find the Lyapunov function or certify that it does not exist. This leads to a counterexample guided synthesis method. in which the learner proposes a Lyapunov function candidate from the localization set, and the verifier either verifies the candidate or rejects it with a counterexample. In this illustrating example, the learner first proposes P0, which is a feasible point in the localization set f tilde 0, as a Lyapunov function candidate and passes it to the verifier. Since P0 is not the target in the target set F, the verifier rejects it with a counterexample added to the sample set, which also refines the localization set to f tilde 1 by removing a fraction of f tilde 0 from the search space. This process repeats until a Lyapunov function candidate is validated by the verifier. However, a caveat in this process is that although we keep refining the localization set, the improvement at each iteration may be minimal, and it may take forever for a learner to find a feasible point in the target set, even if it's non-empty. To address this issue, we propose a design of learner according to a variant of cutting plan methods from convex optimization called the analytic center cutting plan method to provide a termination guarantee. In this method, the learner always proposes the analytic center of the localization set as a Lyapunov function candidate to the verifier. The analytic center is obtained by solving a finite-dimensional convex program shown here. The analytic center is intuitively the point that is maximally distanced from all boundaries of the localization set. In this illustration, the learner sequentially proposes P0, P1, P2 as the analytic center of each localization set and finds a Lyapunov function with P2. As shown in this figure, choosing the Lyapunov function candidate parameter as the center of the localization set guarantees that there is always a large enough portion of the localization set removed, no matter how the cutting plan or the counterexample is chosen by the verifier. After computing the analytic center, the learner then queries the verifier module to validate the proposed Lyapunov function. To validate that a given analytic center returns a valid Lyapunov function, the verifier must maximize the Lyapunov difference function over the region of interest, as shown in the lower part. We denote the optimal value of this optimization problem by P star. If P star is less than or equal to 0, then we have a certificate that the Lyapunov function decreases everywhere and we can terminate the method with a valid Lyapunov function. Instead, if P star is greater than 0, then the optimal solution X star is a counterexample at which the Lyapunov function candidate increases. In the next round, this counterexample X star is added to the set of samples, which can be interpreted as adding a new hyperplane that separates the invalidated P from the target set F. As pointed out in the previous slides, the verifier must solve the non-convex optimization problem on the top. We can reformulate this using the definition of the graph of F, where the pair xy must lie in the graph of F. We argue that for a wide class of hybrid systems, the map F admits a mixed integer representation as shown in the middle. In this representation, the graph of F is described as a level set of a linear function of an integer and continuous variables. Here, x and y are the original continuous variables, lambda is a vector of additional continuous variables, and mu is a vector of integer variables. After using a mixed integer representation of the vector field F, we can reformulate the non-convex problem of the verifier as a non-convex mixed integer quadratic program, which is shown as follows. In this formulation, we maximize the Lyapunov difference function, which is a quadratic one, over the initial state x0 inside the region of interest. We exclude the origin from our search space by using an L-infinity norm ball as a guard around the origin. With this guard, a validated Lyapunov function by the verifier certifies that all trajectories converge to a neighborhood of the origin of the size similar to the chosen L-infinity ball with radius epsilon. The last line of constraints in this formulation encodes the dynamical constraints between xi plus 1 and xi. This form of constraints can be easily extended to describe the interconnection of hybrid systems through their individual mixed integer representation. Although the obtained formulation is non-convex, in practice it can be solved to the global optimum through solvers such as Groupie. You can find more details on this formulation and its solvability on our paper. Overall, our method enjoys a finite-step termination guarantee on the assumption that the target set contains a full-dimensional ball of radius epsilon, which can be any positive number. Our main theorem states that the proposed iterative algorithm based on the analytic center cutting plan method terminates in a number of iterations proportional to n cubed over epsilon squared, where epsilon is from our assumption and n is a dimension of matrix P, or equivalently, the dimension of the basis vector of the Lyapunov function candidate. Finally, we show the efficiency of our method through some examples. In the first example, we consider an LTI open-loop unstable system with 4 states and 1 input. We consider that the system is controlled by a finite horizon MPC controller with quadratic functions and polyhedral state and input constraints. In this setting, it is well known that the MPC controller is a piecewise affine function over the polyhedral state space. For the specific example we studied, the MPC controller has 193 partitions in the state space. The region of interest in this example is chosen as a domain of the MPC controller, which is a bounded polyhedron. The closed-loop dynamics is invariant to on this domain, with Lyapunov function candidates of order k equals to 1, which means that they are essentially piecewise quadratic functions. We are able to find a Lyapunov function after 7 iterations, which satisfies that the stability of the MPC-controlled system. The total running time of this example is 680 seconds, and the figure shows the accumulated running time in each iteration. On this slide, we show that when more than one mixed integer representation of the dynamical system is available, the complexity of our method depends on the specific mixed integer representation applied. In this MPC example, we can either represent the MPC controller explicitly as a piecewise affine function through the explicit MPC methods, or encode the MPC controller through a linear complementarity system derived from the KKT conditions of the finite horizon optimal control problem. In the following table, we compare the running time of our method on a 2D open-loop unstable linear system with an MPC controller. As shown by the rightmost column, although our method finds a Lyapunov function of order 2 in both representations, using the linear complementarity system representation is able to cut the total running time to around 1/10 of that of the piecewise affine representation. The accumulated running time in this 2D MPC example is plotted in the figure, where the time is shown in log scale. On this table, we also compare our method with the standard linear matrix inequalities-based method, which aims to synthesize Lyapunov functions for piecewise affine systems. The LMI-based method first identifies all the state transitions between the partitions of the piecewise affine system in pairs, and then formulate an SDP to synthesize a discontinuous piecewise quadratic Lyapunov function. It verifies stability of the 2D closed-loop dynamical system efficiently in 39 seconds, but it encounters numerical issues with the mosaic solver in the 4D case, which is likely due to the degenerate feasible set of the resulting SDP. However, in the 4D example, our exam method is able to verify the closed-loop stability based on the linear complementarity system representation. As a second example, we considered an inverted pendulum with elastic walls. This system is a nonlinear hybrid system with 2 modes. The first mode is in contact with a wall, and the second is not in contact with the wall. After linearizing the dynamics at the equilibrium point, we obtain piecewise affine approximation of the system and design hybrid MPC controller with state and input constraints. Since hybrid MPC controller is hard to compute in real time, we compute the outputs of hybrid MPC offline and then use supervised learning to approximate it by training a ReLU network which is fast to evaluate online. The overall closed-loop system is a ReLU network plus a piecewise affine system, which can be described using a mixed integer formulation. As commented before, the piecewise affine representation of the closed-loop system is unavailable to us due to the complexity of the ReLU network. For this closed-loop system, we find two Lyapunov functions of order 0 and order 1 and plot the results in the left and right figures respectively. Order 0 corresponds to quadratic Lyapunov functions, and order 1 corresponds to piecewise quadratic Lyapunov functions. To decide the region of interest in this example, we first sample initial conditions uniformly over the domain of the system, and set the reference region of interest as a convex hull of the initial states which converge to the origin. Then we tune the size of the reference region of interest to guide our search of Lyapunov functions, and intuitively, a larger region of interest will give us a larger estimate of the region of traction. In these two figures, the largest region of interest found is marked by the red lines, and the blue lines depict the estimated region of traction given by the synthesized Lyapunov functions. The sampled trajectories of the closed-loop system are plotted too, with the white dots denoting their initial conditions. As you can see, by increasing the order of the Lyapunov function, we are able to find a larger estimate of the region of traction at the cost of longer running time. In summary, we proposed a sampling-based method to find the Lyapunov functions for hybrid systems that admit a mixed integer representation. We briefly mentioned that a wide class of hybrid systems admit such a mixed integer representation. Our method is guaranteed to terminate in a finite number of iterations under mild assumptions. In the verify module, we need to solve a non-convex MIQP which is not scalable. For future work, we will focus on scaling up the MIQP and improve the runtime of the verification step using heuristics such as warm start. Thank you so much for listening to this talk.